This video is supported by the National Science Foundation.
Hello, my name is Daniel Capecci, and I am a PhD candidate at the University of Florida, working in the Florida Institute for National Security. Welcome to this tutorial series on deep learning for integrated circuit reverse engineering. In the first part of the series, we'll be working through an image classification task using PyTorch and the ever-growing Python ecosystem used for artificial intelligence and machine learning. So first, I'll make a quick comment on why deep learning in integrated circuit reverse engineering. Really, the reverse engineering process comprises of complex stages, complex tasks: delayering, imaging, annotation, netlist extraction, and often requires a lot of time and effort from subject matter experts who specialize in reverse engineering. And the current state-of-the-art practices are still fairly tedious and expensive. Requires a suite of clean rooms, microscopy equipment, long imaging times, and the steps are still manual or semi-automated. So there's a need for fast, fully automated reverse engineering. On the flip side, in deep learning, there has been tons of advancements in image segmentation techniques, region of interest detection, and image refinement. In gaming, we see some of the more recent GPUs have this very good capability of creating super resolution images very, very fast. So these computations and the ability for these artificial intelligence models and algorithms to produce high quality imaging output has really caught the attention of a lot of different industries. And integrated circuit reverse engineering is no different. So our objectives for this first part, to work through our image classification task with PyTorch. In this initial part of the series, we'll really focus on implementing our models and the training loop to make sure we understand that, get a good sense of exactly what's going on, how we can do some good logging to make sure we can track our learning curves, our loss curves, convergence checking to stop training early once our model has converged, so we're not training a ton of extra epochs. We'll use a data set that comes from Torch Vision, which is a part of Torch, to start with. We'll defer implementing our custom data set to the second part. And then we'll have a quick discussion and some techniques for visualizing our model predictions with a confusion matrix, so we can see how many times we're classifying correctly in a nice, easy to digest summary. And then a discussion of looking at the model's prediction probabilities. What is the distribution of scores I'm getting after training? And we'll have a discussion of how to interpret that. What I'm assuming you know at this point is you've watched or you've gone through our prerequisite materials, supplementary materials. So you have a sense of what matplotlib does, what the general ideas for how to implement PyTorch. You've seen it at least one time, so I'm going to go a little bit faster through some things. And that you have a basic intuition for what a neural network is, what it does. We're not going to go through the basics of neural networks, but we will assume that you have that intuition. You understand what you've heard of the backpropagation algorithm. You know kind of what's going on. If you don't, I highly recommend taking a look at 3Blue1 Brown's series of videos on that. I think they're great visualizations and a great description of the backpropagation algorithm, how these weights are getting updated in the neural network. We have some other links in the supplementary materials as well. I'm also assuming that you have a familiarity with Python, managing virtual environments. You've used Conda or Mamba, pip in some you've practiced at least, and you have some exposure to object-oriented programming. That may seem out of left field. However, the way that a lot of machine learning algorithms are constructed in Python requires an understanding of object-oriented programming, because we'll be using classes, subclasses, overriding particular methods, and having an intuition for how to connect those concepts in code can be super useful, because it can create a lot of very powerful code that you can quickly change, you can quickly modify, and get entirely different models and entirely different structures that you can iterate and test and experiment very quickly. So if you have a good intuition for those, it'll make a lot more sense for why we're writing the code the way that we are. And we have some links in the supplementary materials to give you some extra support if you don't have that intuition already. So a little quick summary, just to make sure we're on the same page as the tools that I'm going to be using in this series. I'll be using PyTorch, obviously, and instead of using Jupyter Notebooks directly, I will be using Visual Studio Code, which has a Python and Jupyter extensions that allow me to work with Jupyter Notebooks right in Visual Studio Code, as well as what they call the interactive window, basically, where I can use in a normal Python script, I can use some comment pound notation to indicate a Jupyter cell, and I can run just a section of Python code. But I don't need to be working in a full-fledged Jupyter notebook. This has some benefits for working with in an IDE that has code completion, documentation, linking to things, code checking, some static type checking from Pylance, and some other features that I think are beneficial. So we're going to try to expose you to using it in this way a little bit. And then I'll be using Mamba primarily, which is a drop-in replacement for Anaconda and/or pip. You can use pip within Anaconda environments. But as you see me typing Mamba or installing packages with Mamba, it's the same as Anaconda. You can just change the word Mamba for Conda, and the commands will pretty much be the same. And with all that said, let's jump into the code. All right, the first thing we want to set up is our VS Code environment, Visual Studio Code environment. I've already created a folder in my projects directory called NSF-ICU tutorials, and open that folder in VS Code. I already have my data directory with our SEM images in it, even though we won't be using that for this particular part of the series. And I have a utils.py file that has some extra utility helper functions that we'll use throughout the series. And the first thing I need to do is to install my Python and Jupyter extensions, which I think I've already installed them, but I'll double check. So just search for Jupyter, and we want the Microsoft.com version of it, a verified version. Installing Jupyter, this is already installed for me. Install that and install Python extension. And we'll install that. Again, it's already installed on my system. If you just install both of these, we should be good to go. And then the first thing I want to do so with those extensions installed, we need to create our Conda environment. In the supplementary materials, there's some instructions on how to install Conda or the MiniForge package, which will include Mamba. I have MiniForge installed here, and I've already installed that, and I'm already in, as you can see, the default base environment. I can do Mamba mbut-list, and I can see that on this system I have a couple different Conda environments I'm working with. To create a new environment, I'm going to type Mamba, create -n for the name of the environment, and I'll call it IC Reverse Engineering, and I'll install it with Python 3.11. I'll add a -y to just accept the prompt of saying, do you want to install these packages? I can say no sometimes. Sometimes I do that when I want to double check that dependencies aren't going to conflict, but in this case I know I'm okay. And then I will immediately after that command, I will run Mamba activate ICRE. So that will, in one go, it'll first install everything, finish that command with a semicolon, and then run the next command, which is Mamba activate ICRE. Okay, so now that the Mamba activate ICRE has already been run, I can see that I'm actively in my new environment. And I will install my dependencies. So here I'll install first PyTorch, Mamba install PyTorch, Torch Vision, Torch Audio, and I'm installing PyTorch CUDA, the 11.8 version. On this system I have an NVIDIA GPU compatible with CUDA 11.8 from the PyTorch channel, an NVIDIA channel, and I'll add the -y again to automatically accept the installation. Okay, now that that is done installing, Next thing I will do is install my final dependencies. And then next we'll install we'll install Jupyter, Matplotlib, NumPy, Pandas, Seaborn, TQDM, scikit-learn. So Jupyter is the package that will help us, that actually installs the Jupyter kernel, the Jupyter notebook, those toolings. Matplotlib is a library for plotting, NumPy to work with data arrays, vectors, tensors, similar to Torch, just not machine learning oriented, and NumPy is really only on the CPU. Pandas is a data science toolkit for dealing with data frames and tables of data. Seaborn is a plotting package that is a wrapper around Matplotlib that has some extra helper functions to make it a little bit easier to plot. TQDM is a progress bar, more or less. It helps us print progress and how we're doing during training. And then scikit-learn is another machine learning library that is has a ton of different algorithms implemented in it as well. However, those are focused on, again, CPU. They're not necessarily able to run on the GPU all the time. So I'll install those. And just to make sure that our environment is set up properly, I'll quickly run ipython-c, which will allow me to pass in just a command to run. Now I'll import Torch, and I will type torch.backends .cuda.isBuilt. And because it was successfully imported, I have access to Torch. I have PyTorch where CUDA is working, and I get the true Boolean printed out to the console. So next I will create my working Python script. I'll right click in the Explorer, File Explorer, hit New File, and I'll type part1.py. And so now I have a new Python file to work in. VS Code has already recognized that it is a Python file. This down here, it tells me what Python VS Code has detected and is going to try to use as we're working with our code. But as you can see right now, it is not my environment. It is not pointing to the Python from my ICRE environment. So I can do one of two things. I can click here and automatically try to select the interpreter, or I'll select it now, I guess. I can select the ICRE, and now it updates on the bottom right here that I'm using that. If you don't click there, you can also do Shift-Command-P, pull up the command bar, and type in select interpreter, and that same command will result in the same window popping up, and you can select your interpreter from there. If by some chance that VS Code hasn't detected your new environment during that process, you can you can restart VS Code, and I think if sometimes there's a refresh button on the top right that you can click. I'm in full screen mode and it might not be showing up for me right now. And then on the restart though, VS Code should do a better job of detecting your environment. And now to show you how Jupyter cells work inside of VS Code. Here I'm working with a normal Python file, not a Jupyter notebook directly. I can work with Jupyter notebooks. However, to get cell-like behavior, in this case, I can just type ##, and VS Code, because I have the Jupyter extension installed along with the Python extension, it detects that I want to use a Jupyter cell. And I get this nice UI where I can run cell, and I'll do import torch, and I'll do again the same thing we did to check cuda.isBuilt, cuda.backends.cuda.isBuilt. And I can click on run cell to run that cell, or I have a keyboard shortcut set up for myself using Vim bindings. So I can use that keyboard shortcut to just run that cell. And I get the same output where Torch imports, I get this new window, an interactive one. It connects to the VS Code in the backend is creating a Jupyter kernel to connect to, and I'm interacting directly with that Jupyter kernel through these cells. Now let's jump right into our training script. I'm just going to bring in some imports to save time. So I'll quickly go through these. Path is a class that helps deal with file paths. It makes it a little bit easier to work with them. I'm importing matplotlib, numpy to deal with some numpy arrays, pandas for wrapping our data so that makes it a little bit easier to plot with Seaborn, importing Torch and Torch Vision. And I'm also importing dataloader and random split, which are some helper utilities for us to build that loading pipeline for our data set. tqdm.notebook is this helps us print those progress bars, and I'm importing some utility helpers that we have implemented, some custom utilities. So here I am getting the device that I will be working on. So in order to get the benefit of using my GPU, I need to explicitly tell PyTorch to move the model, the parameters on the model, the entire model itself, onto the GPU, as well as each tensor or piece of data that I want to compute over on the GPU. So to do that, I will get a pointer or a reference to that device using a helper utility that we wrote. You can see, it's just a couple if statements looking for the appropriate device, checking to see what's active. And I can run this cell. And I can see that, okay, I successfully detected that I'm working with a CUDA device. And I'll create a new cell by, again, adding hashtag ##. And the first thing we want to do is grab our data sets. So in this case, I'm going to go quickly through the data sets because I want to focus on the custom data set in the next part. So here in this, we'll load our data set quickly. I'll step through the code a little bit here, and then we can spend more time working on the model code. So here I'm just defining using that path class. I'm getting a path to the directory that we want to use, that we'll be saving the data to, automatically creating that directory if it doesn't exist. And then I'm getting a string version of the data directory to be used to pass into my initializers of the CFAR10 class. This transform is what I define. I can use Torch Vision's transforms to compose. So I can pass an array of transforms, which will be each image that I load from my data set will be pipelined through this. There's all kinds of things I can do in here. I can Torch Vision transforms. I can do random augmentations. I can choose random text. I can actually even do a random choice of other transforms. I can do random flips, random horizontal flips. So it can you can actually create a lot of cool augmentations to your data if needed. So this pattern is very powerful and flexible to do a lot of modification to your data with a single pattern, a single list of transforms. And here I'll initialize my CFAR dataset. I am giving it the root directory of where to save it. I am setting the download flag to true, so to download that data if it doesn't exist. If this was false and it didn't exist, it would just fail. It would just raise an error and tell us, hey, the data doesn't exist. And here we're getting the training split of our data set. And then I'm setting the transform for the data set so that every time that it loads an image, the transform will automatically, or the image will be passed to this transform and turned into a tensor. I'm then using the random split helper function from PyTorch to create a training split and a validation split from that overall training split. So in this case, I have a 70% split for training and a 30% split for validation. And then I'm doing the same exact thing to get my test split, and instead just passing the train equals false, and that will allow me to get the testing split of CFAR10. And this is in the documentation. If you look at Torch Vision's documentation for this class, there's other data sets that you can use that follow a very similar pattern. So this is actually a very useful thing to be aware of so that you can run tests on a bunch of different data sets if you need to. But this is the general pattern for working with Torch Vision data sets. And I will run this cell to make sure that we load everything okay. Great. And I see that I have 35,000 training images, 15,000 validation images, and 10,000 test images. And now we can take a quick look at some of that data. So here I'm getting the second sample. I'll get the first one just for fun. And on the CFAR 10 object, there is a property class to index, which is a mapping of classes to the index, so the integer value that they have on their labels. I'm grabbing a holder, I'm keeping track of that, and I'm also creating another mapping of index to class. I'm just reversing that mapping so that I can see both, that I can have lookups that go from integers to the class string value and the string value to the integer value. And then I'll use that to set a title for my image. And I'm using this imshow function from our helpers. And so we can see that these are fairly low resolution images. I believe they're 32 by 32. In our first instance here, we have class 0, which is an airplane. And I'll also do a grid of a bunch of images. And so here I am looping through for 36 images. I am grabbing the ith image sample, and each CFAR, when I index into the CFAR training set or the training data set, it returns a tuple of image comma label. So in this case, when I'm indexing to the 0, I'm getting the image or the 0th tuple of that ith sample. On that, and so I can see the first 36 images that I have in the training data set. And again, they're small, low resolution, 32 by 32 images. But this is a quick way to say, okay, this is what I have in my data set. My data pipeline is working well. I'm able to get images. It's a good sanity check. The next thing we'll do is actually see how much of what we have, how much of what we got. So let's take a look at our class distribution. Now this is a already curated data set, so we can anticipate that the classes will probably be well distributed, as in I have around the same number of instances per class. But in a lot of real world data sets, it's not so clean, especially when you're working with a new data set. You may have a lot of class imbalance, which is something to consider. So this is an important step whenever you're starting out with a new data set, to sort of make sure you understand what's inside of it. And so to create this plot, I am just iterating through the test split, the training split, and the validation split, and pulling out just the labels, just the label of all the samples. And I'm creating a dictionary where each dictionary has only 2 keys in it. It has the split, the name, and the label value. And then I'm creating a single large list of those dictionaries, and then wrapping all of those dictionaries into a data frame. And if I quickly just show you what that looks like, we'll run that. And then if I come over here, I can interact directly with the kernel as well and get the first few values of my table. And I have this nice data frame with 2 columns in it for each key of my dictionaries to work with. And that makes it very easy to pass into this Seaborn plotting function, displot, where I give it the pandas data frame. I just say what I want to plot on the x-axis, which is the label, and I'm going to set the hue, the color of my plot, to be based off of the values of the split. And this multiple sets up how the histogram will be laid out. Will it be on top of each other? Will it be side by side? And actually, I think I'll do stack. I think that might be a little bit easier to see. I'll change that. And then I'll run this plot. Yep, and we can see how our splits are distributed, right, for each class. So each class here being an integer. So this is the 0th class, the 1 class, the 2 class. And I can see that I have a pretty even distribution of my classes within each split. So my train split has about the same number of instances per class, same for validation and same for test. So this is a fairly well balanced, assuming the labels are correct, which is also another thing to check if you can. We're not going to do that today, again, because this is a curated data set, but sometimes things can be mislabeled and that can cause problems in training and data leak as well. And finally, for our data, let's create our data loaders. So for PyTorch, we're setting our batch size. So how many images are we going to load per batch? And these data loaders, the job of the data loader is to wrap a data set and to handle the loading and batching of those images. So the data loader will use the dataset class and grab the next batch, and it can do that with multi-processing, parallel processing, multi-threading, can help us distribute the data to different GPUs, things like that. we can write our custom. It uses a collate function, which we might touch on in the next part, to handle that batching. You can override. You can implement a new collate function, so you can have a lot of customization as to how you're loading and batching your data. The data loader for training will also shuffle the data set. For test, we will not shuffle. For validation, we will not shuffle. But for each of our data sets, for each of our data set splits, we will wrap them in loaders that we will then use during our training loop to grab our batches and our labels. And we can get a sample of our training data set by wrapping our loader or wrapping it in an iterator and just calling next on that iterator. And we'll get a tuple of our batch, which will be a batch of images and a batch of targets or labels. And we can I'm just going to print out the shape and the data type to take a look and see what we see. So after running that cell, I can see that I'm loading we set our batch size to 64. I'm getting a batch of 64 images. The shape of that tensor of our images is 64, our batch size. 3 is the number of channels. I'm loading color images, so I have an RGB channel. And the height and width of the images are 32 by 32, and it is a float 32 tensor. The targets or labels is a batch size of 64, so it's just a single vector, single tensor list of numbers that are integers. So the labels are just 0 through 9, as we're already aware. And now we are ready to start implementing our model. And to do that, I need to subclass the torch and then module class, then .module. And I need to implement 2 methods, the init method and the forward method. And the way that works is I can use this, the initializer to initialize the model, and then the forward function gets called as when I'm using the class that I've instantiated as a function. So in this case, I'd say my model equals MLP. So I'm instantiating my model class, and it is calling the init function on this line 118. And then when I'm ready to pass data to it, say I had a tensor called X, I would get my model output would be the model and the input. So I'm calling this model as though it was a function, and what will happen on the inside the module is the torch module. Normally you'll see in Python, you'll see this method, and this can turn any class, any Python class, into a callable class. And what a torch module does is it uses this inside of this call function, it will call the forward function. So all we need to do for our MLP class is to implement these 2 methods, and we should have a usable model. Now I'll just comment these guys out. And the first thing I'll need to do inside the initializer is to call the super init, so the initializer of my super class, the NN module class. And I'm going to also create some parameters here, some input parameters, which is the number of input features, the number of classes I'm going to be predicting, and the hidden dimensions of my linear layers. And I'm going to have that set to a default of none. So the first thing I can do is just keep track of my int features and the number of classes that I'm going to predict. And I will say hdims equals hdims if hdims is not none, else by default I will pass in 128.256. So if I don't pass any hdims in, by default I will use the values 128.256, which means I will be getting a linear layer of 128 and then a linear layer of 256 neurons. So that's the width of those layers. And the way I can implement this programmatically is to say, all right, I'll start with the number of features. To start with is the in features. And then for hdim in self.r in hdims, I will, first actually I need to create the layers that I'm going to be iterating in. The first layer needs to actually be a flattened layer. Because what I need to do is take my image, which is 3 by 32 by 32, and flatten it so it is a matrix of 64 by 3 times 32 by 32. So it'll just take those, each image in each batch entry or instance will be flattened to a single vector. So I'm just taking in each image and just stretching it out to a single vector. And the end features will be that. And I can say, now I'll say layers dot extend, and I will pass in another list of torch dot n dot linear, passing in a linear layer where the in features are the number of features, and the output will be the HDIMs that I'm iterating over. And then directly after that layer, I will add a ReLU activation function. And then after that, I will update the end features for the next iteration using the HDIM that I already have. So the output or the input of the next linear layer will be the output of this linear layer. And then at the end, my last linear layer, number of features that were out, the most recent number of features, and the number of classes I'm going to be predicting. So that last layer will be outputting only the number of classes that I want to predict over. And I will add, and I will not add. I'm not going to add an activation function here because I'm going to be outputting the raw. So I'll do this. I will do another ReLU here. And with that, I will wrap all of these into my model, which will be a property on my n.module. And that's going to be wrapped in a sequential module. And I will expand my layers, my list of layers, into that sequential module. So now I have my model on this property. Finally, what I like to do is to make sure that as a sanity check, I will create an example input of a random tensor that is of the shape single entry of batch, the number of channels that or the number of in features. Right, so this is a sample of input that I'm passing into this model. And I will get the output by just passing that into my model. Example input. And then I will print that shape of my output to make sure that it looks the way that I anticipate. It's also a useful debugging tool that every time you instantiate a model with a certain set of parameters that you are actually getting the outputs that you anticipate. And then for the forward implementation, I will get my logits just by forwarding in the input and returning those logits. The reason I'm calling this logits is because the output of the, actually I should remove this. The output of the model without the activation function is is often referred to as logits. If I add an activation, it'll be more often referred to as the actual prediction or probabilities. Usually that last layer will be something like a softmax. I could manually add the softmax here, and that would apply the softmax activation function to that output, making the output a probability distribution so that it sums the 10 classes I'm predicting, the 10 numbers, will sum to 1. However, in this case, when we write our training loop, I'll be using the cross entropy loss, which does that softmax inside of it. So I'm going to be just returning the logits here, which also gives me flexibility that if I want to change or modify or get the raw output of my model, I can do so in the future. And then I can always apply an activation function that I'd like later on in my code. And so now let's actually run this guy. And so now I need to pass in the parameters. So my in features are going to be the flattened size of my images. So really it's 3 times 32 times 32. That will be the number of features I'm taking in after the flattening of my images. The number of classes I'm predicting is 10. The CFR 10 dataset has 10 classes we're predicting. And I will leave the HDIMS to default, but I'll put that here. And then we'll get another sample input. Here, I'm not really worried about the actual values. I'm just making sure that all of my shapes make sense. So I'll run the cell with the model implementation and the initialization, which should print out just the shape of the output after passing in my example input. And I run that cell and it looks great. I have a single batch and 10 numbers and nothing failed, everything worked. And now I can run the print model and I can actually see what was built in that loop, right? So I have defined two HDIMS, two numbers in my HDIMS. So 128 and 256, those were the default values. And this 3072 is the result of multiplying 3 times 32 by 32. I can see that I have bias set to true. That is a default for linear layers. So it has that bias value. So it's, you can think of it y equals mx plus b, right? Where the m is the weights of the linear layer. The flattened layer flattens out my image. So I'm passing in, here in my example, I'm passing in an example input that already has the number of features. So it's still just flattening it. But in order to make sure that I can even flatten my images, I'll do what I was going to do before. And I can do 1, 3, 32, 32. And if I out equals model x, I'll run that. And that still works, right? Because if I give the model something that has already been flattened in those starting from dimension 1, so I should mention that by default is flatten, takes in dim, or the start dim, and it defaults to 1. And that means it will start not from the batch, which is the 0 dimension. It'll start from dimension 1, which will be the 3rd, or the 3 in our case. It'll be 3, it'll flatten 3 all the way to the end. In the case of passing in the number of features that I had in my initializer, so here, the result of flatten is the same as the input already was. It doesn't need to be flattened more. It doesn't really do anything in that case. But I could also do 3, 32, 32 here, and it would still be okay. I'll run that again, and everything works. Now, the one challenge here is that if I run this and I change the size of my input, if I change this to 64, 64, this would break. Should break. And it does because now I'm giving it an example input that it does not expect. So another way to maybe write this class would be to say, how big is my image size? How big, or I can say image shape. And I can expect that to be a tuple. So in this case, now what the n features would be is I can use np dot product of np array image shape. So when I pass in that shape, it'll just multiply all those numbers together, however many numbers I have, and then use those as the number of in features. So this makes my code a little bit more flexible. Instead of specifying the exact number of features, I can now specify in my initializer the image shape that I have. Instead, now I can automatically calculate that. And here I can do image shape so that example input it creates in the initializer is the exact same size of the images I'll be passing in. And I can run that. And now everything is calculated for me. And my model is being built based on these hyperparameters, which is very useful for as I iterate and run experiments. Okay, I think I've belabored that point sufficiently.